Let's get back to example. Continue with our class. We finished Newton's law, and then we try to apply Newton's law to different kind of motion. For example, we have a system of mass and pulleys on the class yesterday, and we're talking about the motion in uniform circular motion, force in uniform circular motion. And there are two or three examples out of it. For example, the conical pendulum, or the making a turn on horizontal road, in which the force that involved in that motion is the friction force. And also we talking about another methods of moving around the curve, and that is called the banking. So in many cases, if you watch the racing, cars racing, either in cartoons form or actual form, you will see that in the racetrack, on the outside of the street, they bank it up to create a ramp that the car can travel at high speed into the curve. Okay, and that banking say that the maximum velocity is depending on the angle theta. So V max is square root of RG tan theta. And in motorcycle also, if you're going fast and you're going to the curve, usually the one who ride the motorcycle will tilt their body a little. We don't see much in everyday life, because in everyday life, we don't go that fast. But still, if you're riding a bicycle or a motorcycle, sometimes when hitting the curve, you feel that. Now, so let's take a look at another example that relate to that two special case. First one is for a car to make a turn at 72 kilometers per hour or around 20 meters per second on the flat road with coefficient of static friction of 0.8. What is the suitable radius of curvature of the road? Okay, now this is the flat horizontal road. So the only force that pull the cars in the track is the friction, and it is static friction. So according to this, the static friction is always lesser than mu s times n, or lesser than mu s times mg. The maximum value speed that the car can travel is when the whole friction force is becoming the maximum value of friction force is totally the centripetal force. So Fs equal to mc, and you get mu s times mg equal to mv squared over r, and that is V maximum. Now the mass cancel each other, and then you have V maximum square equal to mu s times radius of curvatures of the road and times g. And the problem said for a car to make a turn at 72 kilometers per hour or 20 meters per second. So we know that the maximum value of the car is 20 meters per second. Mu s is 0.8 and g is 50 meters per second. The radius of curvature of the rod will be V max square over mu s times g, or 20 times 20 divided by 0.8 times 10. And that gives you 400 over 8, and it is 50 meters. So the radius of curvatures of the rod should be around 50 meters. And that is the reason why sometimes you see that why the rod have a little long curve. Okay. The longer the curve it is, the faster the car can travel. Okay. So for a expressway, you can have a small radius of curvature because you have to reduce speed a lot during to make a turn. One example of that, I'm not sure how many of you notice it. When you take an expressway from Phan Ram 9 and trying to get to the Phan Ram 6 on the second stage expressway, you're traveling from Phan Ram 9 and then passing Anusawari Chai, there will be right turn towards the Prachachun and then left turn towards Yomaraj. And if you take a notice, when you make a right turn towards Prachachun, you will see that on the ramp, on the side of the road, there are scratch marks, plenty of scratch marks there. And the reason is if the traffic is, well, not congested, the cars usually come with high speed, and that curve is designed to be slowed down at the you must have maximum velocity at least, I think, lower than 80 kilometers per hour in order to survive to going into the curve without getting split off. Now, at night, a lot of cars going into that curve with, well, much higher speed than that recommend. So they will slide off and then crash themselves to the ramp. So that's the problem. Many people drive too fast, faster than speed limit. And they don't realize that negligence is harmful to themselves and to others. Now, let's take a look at another example. For a 100 meters turn, if you want the car to make a turn at 30 meters per second or 108 kilometers per hour, find the banking angle of the road. So in this case, you have a radius of curvatures of the turn to be 100 meters. And the cars should have traveled along this curve with maximum speed of 30 meters per second or 100 kilometers per hour. That usually not working with only friction alone. So in this case, we have a banking effect. So we bank the outer edge of the road up by the angle theta. By doing that, the normal force on the car is going to tilt from vertical by the same angle. So it's tilt by angle theta. And the weight of the car is still there. You can break the weight into two forces, but it's not help. What I do is I break the normal force into n cosine theta, and that equal to mg for the car to be stationary on the ramp, and n sine theta to be centrifugal force, centripetal force. So we have n cosine theta equal to mg and n sine theta equal to m times centripetal acceleration. So it's mv squared over r. So divide the two equations, we get mg tan theta equal to mv squared over r. To get rid of the n, okay, n equal to mg over cosine theta. So we have mg tan theta equal to mv squared over r. Mass and mass cancel. And we say that tan theta, which is the banking angle, is actually v squared over rg. And because the velocity is 30 meters, so v squared is 900. The radius of curvature is 100 and g is approximately 10. So we have 1,000 downward. So 900 divided by 1,000, it is 0.9, or the banking angle should be 42 degrees. So I have made my remarks that the radius should be higher than 100 meters, because in this case, the banking is almost 45 degrees. So if we increase the radius of curvature by 10 times to be around, no, by two or three times to be around 300 meters. So if I is 300 meters, tan theta is 0.3, you get 3 more. And arctan of 0.3 is around 16 degrees, which is more acceptable than 42. Okay. So that's the end of this example. Now, possibly you guessed it already. We are talking about projectile. Projectile, we already talked about the force. We talk about the uniform circular motion with the force and Newton's law relate to it. Now we are going to a force that relate to harmonic motion. Okay. So for harmonic motion, let me review that. It is a motion that going back and forth, complete one revolution by the period t, and having the frequency f, number of complete revolution per seconds. And they found out that for a harmonic oscillation, for a simple one, the motion or a displacement of an object is either a sine or a cosine function. And according to that, we saw that the velocity of an object and the acceleration is either a sine or a cosine with 90 degrees phase difference. But most importantly, the acceleration is opposite and proportional to the displacement. So A is minus omega square x, where x is the displacement of an object, and A is the acceleration. So that is the harmonic motion, a short review. Now, if you find apply Newton's law to that, in order for an object to have the acceleration in harmonic motion, A equal to minus omega square x. So a force, a net force on an object also have to have a unit of MAs, or minus M omega square x. Okay. So in order for an object to move in harmonic motion, so for F to be Kx, let me set up something here. Let's write it around here. According to harmonic motion, A is minus omega square x. X is a displacement. Now, according to Newton's law, summation F must equal to MA. So summation F for this case must be minus M omega square x. Or we can solve that summation F is equal to K minus Kx to be the equation for harmonic motion. So whatever system of force that you use, if your force is negative and proportional to the displacement, that will result in a harmonic motion. Let's place a and one type of object is that is a spring. A spring is a piece of metal that wounds around to make a tube, okay? Moves around in a circle to make a tube. And what happened is that when you pull it out, the spring stretch out by some distance, and then it creates a restoring force by the physical properties of the spring. And that restoring force is pulling the spring backward. Okay. Each of the circle will produce a little stretching distance. So if L0 is the original length of the spring, when you pull it out, we found out that if L0 is large, it can stretch more easier than the short spring. So we found that if L0 is called a relaxing strength length or natural length, It's a spring when there is no force acting on it. If you pulling or pushing it off or pulling it off by the distance x, which is the total length of the spring after stretching minus by the natural length, we found that there is a restoring force F proportional to that stretching distance. And the restoring force always opposite. So we got F equal minus Kx. Some spring having these properties, both stretching and compressing. So we have F equal to minus Kx for spring. And K is called a spring constant or a stiffness constant. And the unit of spring constant, a stiffness constant, is in newtons per meter. Well, let's talk about Spiderman webs. You see that in several movies, Spider-Man's hanging a car out of his web, and his web stretched out by in the units of meters. So in a way that we observation in the movie, his web is equal, can withstand the weight of 10,000 newtons. Usually a car weight is around, a car mass is around 1,000 kilometers. So we are talking about 10,000 newtons, and by a stretching distance less than a meter. So we are talking at the order of magnitude if of 10 to the 5th. Okay, 10 to the 5th newtons per meters of stiffness constant. And actually, there are real substances that have that stiffness constant, and that is a carbon nanotube that can withstand that kind of force. Actually, for actual spider web is strong enough also. But the things of the spider web is that usually it is strand that have very small cross section. So if the spider web is having a large enough cross section, they say that it may be stronger than steel cable. And that's related to that stiffness constant. So if we have a spring connect to the mass on the horizontal frictionless ground, well, I have to say first, frictionless, this means smooth. A mass, the weight and the normal force will cancel each other because they are sitting on the ground. If you pull that mass out by a distance delta x, there is a restoring force F equal to minus Kx. And that according to Newton's law, F equal to minus Kx is ma. So A acceleration is minus K over m. Now, if you recall the acceleration in simple harmonic motion that we discussed earlier, For simple harmonic motion, A is minus omega square x. So omega, or the angular speed, is related to the stiffness constant and the mass of the object by omega is square root of k over m. So let's take a look at this. Okay. In that case, A is equal to minus k over mx, or minus omega square x. And omega is square root of k over m. And the solution of the displacement is in form of harmonic motion. It is x equal to a sine omega t plus phi. Well, a and phi can be solved with what we call an initial condition. So for example, a mass of 1 kilogram was attached to a spring with stiffness constant of 10,000, 1,000 newtons per meters. A mass was then pulled off from equilibrium position by 10 centimeters, then released. Find the equation of this displacement and what is the frequency of oscillation. Now, according to this equation, okay, the object is pulling out by a stretching distance of 10 centimeters and then release. And we were assuming that the maximum displacement that it can be happening is 10 centimeters. So in a way, we start with x0 equal to a sine omega t plus phi, and omega is square root of k over m. In this question, they given us that the stiffness constant of the spring is 1,000 newtons per meters, and the mass of the object is 1 kilograms. So we have square root of 1,000. And square root of 1,000 is 10 square root of 10. Square root of 10 is 3.16 times 10. You get omega equal to 31.6 hertz. Now we can using this because at beginning the velocity is 0. We have another equation for this, because velocity of an object at the distance displacement x can be solved by v equal to omega square root a square minus x square. Now, because at the beginning the velocity is 0, we see that in that case, x equal to a at the beginning. So our displacement at the beginning 10 centimeters become our amplitude. And when t equal to 0, we get x equal to a sine phi, and x is 10, and a is also 10. So we got sine phi is 1. So the angle, phase angle is pi over 2, or 90 degrees. So the actual answer for this is that x is a cosine omega t. Okay. No, I just. Okay. Or you can say that x is a cosine omega t. to be the answer. Okay, someone send a message. Y phase is pi over 2. Okay, let's take a look at this. We proved here that according to the relation, velocity is omega square root a square minus x squared. At the beginning, we say that the velocity when you pull it out by x0, 10 centimeters is 0. So v equal to 0, it means that at that point, x0 equal to 10 centimeters is actually in amplitude. So amplitude is 10 centimeters. Now at t equal to 0, if you put it in here, x0 equal to a sine omega t plus phi, t equal to 0. Okay, omega times 0 is 0, so you have x0 is a sine phi. And because x0 is a, okay, because this is also 10 centimeters and this is 10 centimeters, we got sine phi equal to 1. And the angle that gives the sine function of 1 is pi over 2. So the result is the actual equation is x equal to a sine omega t plus pi over 2, or you can say that it is a cosine omega t. Okay. I hope that's explained this situation. Okay, let's take a look at this one. Okay, this is the same as another example. A mass of 1 kilograms was attached to a spring with stiffness constant of 1,000 newtons per meters. A mass was then pulled off by 10 centimeters, then released. Find equation of its displacement. What is the frequency of oscillation? Okay, this one already did. Okay, related to what happened last example. X is then can be written as 10 centimeters sine omega t plus pi over 2, or x equal to 10 centimeters cosine omega t. Now they ask what is the period and frequency of the oscillation. Because omega is radiant speed or radiant frequency, the angular frequency is 31.6 hertz or in radian per second. We have a relation that omega is 2 pi f or omega is 2 pi over t. So we got the frequency is omega divided by 2 pi, and 31.6 divided by 2 of 3.1415 give you around 5 hertz. Okay. Well, actually round up by 31.6 divided by 3.16 to be around 10 times. 10 divided by 2 is 5. So it is slightly different from 5 hertz. The period of oscillation is 1 over f. So it's 5 times per second. For each time it is roughly 0.2 seconds. And that is horizontal configuration. Now let's take a look at another example. It's also a spring and mass, but then it is a vertical configuration. Okay, could you forgive me just for a minute? I'll need some water. Let's take a 5 minutes break. Let's take a look at another configuration for spring and mass. It is vertical configuration. In this case, as you might already notice, we have to consider the weight of an object also. So suppose we have a light spring, or the spring itself have very small weight. So just a minute. Hello. Back. Let's assume that the spring is weightless. So it is very light and the stiffness constant is K. Now, if you hang spring by itself, well, actually in real life, the spring will stretch out a little because of its own weight. So we call this is a original length, the L0. Then if you're hanging a mass M onto the spring will stretch out until the restoring force equal to the weight. So in this case, if it's stretched out by a distance x0, the restoring force F equal to minus kx0 is equal to the weight mg. So considering only the magnitude kx0 equal to mg or x0 to mg, so k, we call this equilibrium point because it's where the force of the restoring force equal to the weight. And the total length of the spring increased by L0 plus X0. Then if you further stretching it by a smaller distance A, and then let it move, we found that the spring will moving up and down or back and forth around the equilibrium point or around equilibrium length with the amplitude of A. And this is then become a harmonic motion. And it is easier to prove that okay, let's get back again. So if you stretch it out a little, it will just going up and down, and then the displacement here from equilibrium point is in a harmonic motion form. So it's A sine omega t plus phi, where omega is square root of k over m. Okay. You can prove it out that even during vertical configuration, if our x is measuring from equilibrium point, the equation of motion still have the F equal to minus omega m omega squared x, the same as horizontal. So if you have the same spring and the same mass hanging vertically or horizontally on the smooth frictionless surface, we will find that the frequency of oscillation are the same on both cases. The only difference is that the spring in vertical axis is stretched out a little bit further than the spring on horizontal axis because of the weight of the object. Okay. Now, another example of motion in harmonic motion is called a simple pendulum, which is a mass attached to the spring and tilt, making an angle of theta, and then let it swing. Now, we can show that according to Newton's law, when you pull it out by the angle theta, the weight mg is point downward. So you break it into two directions. The mg cosine theta will be countered by the tension in the spring. And this mass is left only mg sine theta downward. Now the force is mg sine theta and equal to ma. So I cancel the am out. So we have, according to Newton's law, the acceleration is minus g sine theta. Now, because of the object is stretching by a distance t, is tied up to a fixed point by a distance t, it means that it cannot move anything further than that length. So when it's moved in a along a circular path. So the displacement, instead of talking in terms of a distance, we can change it into an angle by that the distance or displacement from equilibrium point where theta equal to 0 to be s equals to theta L. Okay, according to this, the length of the chord is related to theta. Now the velocity is omega L, where you take a derivative of this, ds by dt. L is constant, so you have d theta by dt, as we call it, omega. And then acceleration is alpha L, because also L is constant, so you got d squared theta by dt. And alpha is called angular acceleration. So by doing that, we know that the acceleration is L times d squared theta by dt squared. And this is called angular acceleration, the rate of change in angle theta over time. And you see that by putting in this A equal to alpha L, we get alpha is minus g over L sine theta. And this is acceleration equal to minus g over L sine theta. Now, this is not considering a simple harmonic case unless your theta is small enough to be considered that sine theta is approximately theta in radian. This one we have to point out that it must be in radians. So we have d squared theta by dt squared, or the acceleration is minus g over L theta. This is also an equation of motion for simple harmonic, where well, be careful, this omega and this omega are not the same. This is omega of simple harmonic motion to be square root of G over L. Okay. And frequency of swinging is 1 over 2 pi square root of G over L, and G period is 2 pi square root L over G. This is period of oscillation. So a simple pendulum, if you pulling it out from equilibrium point by a small angle, usually what they say is less than 5 degrees. It will swing back and forth and like the simple harmonic. And let me write something here. Okay. And solution, theta is theta 0 sine of omega t plus phi. Okay. In simple harmonic form. Okay. So let's move to a simple example. Find the length of a simple pendulum that have the period of 1 second. A simple pendulum is used mostly in clock, okay? And they decided to be moving back and forth complete in 1 second, or maybe more than 1 second, depending on how fast you want it to go. But it having a constant rhythm. So they use it as a clock for counting the time. So let's take a look at this. What we need is the period of 1 second. So it's complete 1 revolution in 1 second. And we know that for simple pendulum, the period is 2 pi square root of L over G, where G is the gravity. So then T square is 4 pi square L over G square on both sides. And we get L is T square over 4 pi square G's. And then, well, T is 1, so you got 1 here. Now G is 9.81 meters per second, and pi square is 3.1416, and there's some other constant square. And it's turned out to be around 9.85. So usually what we found out, and somebody's sometimes remember, is that G over pi square is approximately 1. Now, you have to be careful here. Only the magnitude without the without the units. The number of G's and pi square in meters per second per pi doesn't have any units. It's 1. It's just the math, the numbers that represent, not the unit. So we turn out that we have length is around 1/4 of a meters, or about 25 centimeters, to give you a 1 second pendulum. And this is also some situation where you can used to measure the gravities of some other planet. Okay, because G is changed by the planet, but the length of the pendulum and the period is not. So when you send this pendulum somewhere else that have the different gravity, you can detect the value of gravities of that planet compared to the Earth directly by measuring the time that it complete one revolution. Okay. Let's work on this question for a little bit. Okay, and then I will give you the solution. Well, this is the second hours of talking, so I start to type a little bit. So let's take some time working on this problem, and then I will give you a solution later. The question say that a spring of stiffness constant K equal to 100 newtons per meters was hung vertically from the ceiling. A mass of 1 kilogram was attached to the spring. How much did the spring stretch after hanging of the mass? And if the system was then set to oscillate, find the angular frequency and period of oscillation. So let's work this problem out for 5 minutes, and then I will give you a solution. Okay. Meanwhile, I will pause the record for time being. Okay, let's get back to this question. The question given the K of 100 newtons per meters and mass of 1 kilograms. How much this spring stretch after hanging the mass? Okay, well, when you hang in the mass, the spring will stretch out until the restoring force equal to the weight. So we get minus Kx equal to mg's, or the magnitude Kx equal to mg's. And K is 100 newtons per meters, and X is a distance stretching, and then you have 1 kilograms times 110, and then you see that 100x equal to 10, and X is 1/10 or 0.1 meters, around 10 centimeters. This is, well, can't help it, but thinking about Spider-Man on both sides, on both cases, the original Spider-Man where Tobey Maguire is playing, and Amazing Spider-Man where Andrew Garfield is playing. Both cases have the car hanging by a web. Okay, and considering the unit, the stretching is in the unit of meters, and the car's weight is around 10,000 newtons. So in that case, we estimate the Spidey web to be around 10,000 newtons per meters. So a little bit 100 times bigger than this one. Okay. Now, let's look. The second question is, if the system was set to oscillate, find the angular frequency and the period of oscillation. Now, if we continue to stretch it a little to have become a harmonic oscillator. So A is minus K over mx. You stretch it a little bit more distance before, after you reach the equilibrium point. And K is 100 newtons per meters divided by 1 kilograms. So you got A is minus 100x, or omega squared is 100. Okay, omega square is K over M, so 100 newtons per meters divided by 1 kilograms. And that is 100 radians square over second square. Take a square root, the angular frequency is 10 radians per second. So the frequency is omega divided by 2 pi, or is 10 divided by 2 pi. And the period of oscillation is 2 pi over 10. So the period is 2 times 3.1415 divided by 10. And you get 6.28 or 6.63 seconds of the period of oscillation. Okay, that's the one. So we get into another topic in which I will start this and then talking about it later next week. Okay. It is about Newton's law and momentum. This is mostly considered the second and third law. Okay. So let's take a look at this statement. According to Newton's law, we have A equal to summation F over M. And this is an actual statement of Newton's law, or summation F over MA. Now, this have some limitation. The limitation is that the mass of the object that moving must be constant. Okay, we don't have anything related to the changing of mass. And this equation will work only in initial frame, or a frame that is moving with constant velocity, that we call a initial frame. There are two types. If you are moving in a case where it's moved with acceleration, for example, you in the car that is accelerate along the road, you actually feel your body compressed to the seat, and that is a force that coming out of nowhere. So in the case that you are in the accelerate non-initial frame of reference, you need to be adjust the equation to compensate for that acceleration. But that is not our topic to talk about this year at this point. So we have this, that in initial frame, suppose that everything is in initial frame. Okay. Now, the acceleration is, by definition, is dv by dt. So you can say that summation F is m dv by dt. Now, because in this case, we say that m is not constant, m is constant, you can pull it into the derivative. So we have summation F is d by dt of m times v. And you see that this is something is the rate of change over time of the other things. This is what it's supposed to be. It doesn't have any constant in front. So by this case, actually Newton's know it, but he didn't call it like we call it today. He called it an essence of motion, something like that. But he also gave a definition that let's call the product between the mass of the object to the velocity. Let's call that momentum. So after we call this, we have that the force acting on an object is the rate of change of momentum, of its momentum of dp by dt. Now your mass doesn't have to be constant anymore because it is a product between mass and velocity. The mass can be changed over time also. So you might encounter the system where you have mass change while it's moving, but the equation F equal to ma will not help you that. But the rate of change, the Newton force equal to d by dt of momentum can help you solve that. So a net force is the rate of change in momentum. Okay, so let's talking about example for this. We're talking about football, or, well, if you say it in American term, you talk about soccer. A football or a soccer ball is moving at the speed of 10 meters per second towards the goalkeeper. Well, he stopped it using his hand. Okay, the ball is moving in with 10 meters per second. You put your hand on it and then stop it within 0.5 seconds. Find the force that the goalkeeper act and the football, given the mass of the football is 0.5 kilograms. Well, this is typical Newton's law application, but then it can be considered in terms of momentum also. You have the ball that initially moving with the speed of 10 meters per second, and then at the end, the ball stopped. Velocity is 0. And the time is 0.5 seconds. And they ask, what is the force? Well, think of it as Newton's law. You have initial velocity, you have final velocity, you have the time, you can find the acceleration. Once you find the acceleration multiplied by the mass, you get the force. So you can say that, okay, let's put it this way. Solved it according to Newton's law. You say that initial velocity is 10, initial speed is 10, final speed is 0, mass is 0.5, and the time interval is 0.5 seconds. From F equal to ma, and a is delta v by delta t, so it's v minus u over delta t. You get a is 0 minus 10 over 0.5, or minus 20 meters per second. Now the force is ma, so it's 0.5 kilograms times minus 20 meters per second. And it gives you minus 10 newtons. And the minus sign states that it is opposite to the initial velocity. That is the solution according to our normal Newton's law. You can prove it with the concept of momentum also. You see that the initial momentum is the mass times the original initial velocity. So it is 0.5 times 10, or 5 kilogram meters per second. Final momentum is 0. You don't have anything. It stopped. So the force is dp by dt. It is pf minus pi over delta t. And it's 0 minus 5 divided by 0.5. So it is minus 10 newtons. So it is the same thing, but it reduced the process by a half. Okay, so you can consider using this one and when solving the problem. But the actual process of momentum, the important things is by comparing the third law and using it in collision. Okay, we have about 3 minutes and you have to study at 2:30. So let's wrap it up over here. See you again on Tuesday. And we will see more of the example regarding momentums and motion. And then we will start collision, okay, in 1 and 2 dimension. Okay, good luck and have a nice weekend. Next week, we're gonna have quiz also on Tuesday, so be prepared for projectile, harmonic oscillator, and circular motion. Possibly not Newton's law yet. Okay, see you on Tuesday.